This section will cover how interrupts are delivered using the virtualization module. The hypervisor can configure the system to deliver interrupts in 3 different ways. First, it can program itself to receive the interrupt directly using legacy methods. It can configure the interrupt to go directly to the guest OS without any hypervisor intervention. It does this in 2 different ways depending on the type of interrupt. I'll go into details later. And last, it can choose to receive the interrupt itself but then pass the interrupt to the guest OS. The virtualization module has to deal with 2 modes of interrupts. Vectored interrupts, where there is a one-to-one connection with an interrupt pin and an interrupt vector pin in the interrupt priority field, or IPL, of the CP0 cause register, or using external interrupt controller that asserts vector numbers into the request interrupt priority field, or RIPL, of the CP0 cause register. The following slides will cover the 2 modes and how each is configured and works with the 3 delivery methods. First, I'll cover the vectored interrupt mode. I'm going to show you the big picture first, and then I'll go into the details on the setup and inner workings of the vectored interrupt mode for virtualization. To start, there are external interrupt sources coming into and becoming pending interrupts. Next, the pending interrupt is checked against the root interrupt mask. And if the mask is set, then the root will receive the interrupt. If it is not, then a pass-through mask is checked to see if it is to be passed through to the guest. If it is not set, then nothing happens. If it is set, it moves along to pending for the guest. The guest interrupt mask is then checked. If it is not set, nothing happens. If it is set, it gets handled by the guest OS. The root timer and the guest timer are handled in the same way. The assignment of an interrupt to root is done by setting the interrupt bit associated with the interrupt pin in the root status IM field to enable the interrupt to root. This interrupt will interrupt the core, place it into root mode, and start executing at the vector for the interrupt. The assignment of the interrupt to a guest is done by setting the interrupt bit associated with the interrupt pin in the guest status IM field and setting the same bit in the pending interrupt pass-through field of the guest control 0 register. The last method of delivering an interrupt to a guest is through the root intervention. This is called root asserted guest interrupts. There are 3 reasons this might need to be done. First, if the hypervisor wants to monitor guest interrupts, it can receive the interrupt and do whatever it needs and then pass the interrupt along to the guest. Second, the hypervisor may want to send a virtual interrupt to the guest, like a pseudo device. And last, when the guest is not resident, its interrupts will be redirected to the hypervisor. When the hypervisor receives an interrupt for a non-resident guest, it will need to context switch the current guest out and switch in the guest that should receive the interrupt and set the interrupt up so the guest will receive it. The next slides will go into how this is done. If the hypervisor is monitoring guest interrupts, it will first receive the interrupt as if it were a root context interrupt. Then it will do what processing it needs to do. Once that is done, the hypervisor will set the hardware clear or HC bit in the root guest control 2 register that is associated with the interrupt pin. This is necessary so the associated bit in the root cause register will be cleared when the associated guest cause bit is cleared by the guest OS when it deasserts the interrupt. Next, the hypervisor will set the associated bit in the virtual interrupt pending field of the root guest control 2 register. Once the guest execution is enabled, the guest OS will receive the interrupt as long as the guest IM field is set to enable that particular interrupt. If the hypervisor wants to cause an interrupt in the guest, it should make sure that the hardware clear bit associated with the virtual interrupt pin is not set, since there was no external interrupt. Next, the hypervisor will set the associated bit in the virtual interrupt pending field of the root guest control 2 register. Once the guest execution is enabled, the guest OS will receive the interrupt as long as the guest status IM field is set to enable the particular interrupt. If the hypervisor receives an interrupt due to the fact that the target guest is not the current guest executing, then the hypervisor needs to first context switch in the target guest and proceed to set the guest up to receive the interrupt. Now I'm going to switch to explaining how the external interrupt controller mode for virtualization operates. The virtualization module requires a guest ID associated with the interrupt. The guest ID will be used to direct the interrupt directly to the root interrupt bus if it is 0, or the guest ID interrupt if the guest ID of the interrupt matches the resident guest. There will be more on guest IDs that don't match the resident guest in the next slide. To start, external interrupts come into the root or guest interrupt bus to become a pending interrupt. Next, the pending interrupt is checked against the associated interrupt mask, and if the mask is set, the associated context will receive the interrupt. If it is not, nothing happens. The root timer and the guest timer are also routed directly to the associated interrupt bus. Now for a look at what happens if the interrupt is for a guest that is not resident. In this example, the resident guest is guest 1 and the interrupt is for guest 2. The external interrupt controller will check its target guest ID against the current guest control 1 ID and see that they do not match. It will then deliver the interrupt to the root bus and write the guest intended to the external interrupt controller guest ID field of the root guest control 1 EID. Then write the guest interrupt priority to the guest request interrupt priority field and write the EIC shadow register set number to the guest EIC shadow register set field. Then it interrupts the root context using the interrupt vector 200 hex. At that interrupt vector, the hypervisor knows the interrupt is for a non-resident guest. The hypervisor uses the external interrupt controller guest ID to context switch to the guest. When the hypervisor has done the swap, it will execute a return from exception, which causes the processor to enter guest execution mode. On guest entry, the processor copies the guest request interrupt priority to the guest context cause RIPL field and the guest EIC shadow set to the guest EICSS field. Once the root interrupt does an exception return, the guest will be interrupted. In systems where there are multiple guest contexts, the hypervisor should maintain a virtual timer for switched out contexts. If the timer triggers while the guest context is switched out, the hypervisor should switch in the guest context. The hypervisor will need to set the timer interrupt bit in the guest cause register before completing the context switch. The guest OS will take the timer interrupt once the guest execution is resumed. There is only one set of performance counters per processor or per VPE on an MT system. These are located in the root context. The hypervisor can configure a set of counters to be controlled by a guest context. The hypervisor enables the guest use of performance counters by setting the guest config1 PC bit in the guest context. It should do this when it starts the guest for the first time and not change this value so the guest can read this at boot time. The hypervisor can control which set of performance counters a guest has access to by setting the specific performance counter event class field. This field is only visible in the root context. A setting of 2 means that only guest events will be counted. The counter is controllable in the guest context, and the counter overflow exceptions will be taken in the guest context. The hypervisor can control access to the core's resources. These next slides will cover how that is done. If the core is configured with shadow register sets, then the hypervisor can allocate them to guest context. It does this by defining a range of shadow register sets for a particular guest. First, it sets the guest lowest shadow set field in the guest control 3 register with the starting shadow set number for the low end of the range. Then, it sets the normally read-only highest shadow register field in the guest's CRS control register with the number of shadow sets being allocated to the guest. The range for the guest starts at GLSS and ends at HSS. The hardware will automatically offset the starting number to the first shadow set for the guest to 0. Note, it will make context switching faster if the hypervisor allocates at least one shadow set to each guest to use as the guest's main general purpose registers, because the hypervisor will not need to save the GPRs on the guest context switch. The high and low multiply registers are shared by both guests and root context, so the hypervisor must save these registers when switching guest contexts. If the DSP module is present, it is shared by both guests and root context. The hypervisor must save the high-low and the 3 high-low accumulator registers if enabled for the guest context. The hypervisor controls a guest access to the DSP module by setting the normally read-only DSP present or DSP revision 2 present fields in the guest config 3 register. When a DSP instruction is issued and a DSP module is not enabled in the guest status register, then a DSP module state exception is taken in guest mode. If it is enabled in the guest status register but not enabled in the root status register, then a DSP module state unusable exception is taken in root mode. If a floating point unit is present, it is shared by both guest and root context. The hypervisor must save the floating point registers if enabled in the guest context. The hypervisor controls a guest access to the floating point unit by setting the normally read-only floating point present field in the guest config 1 register. When a floating point instruction is issued, and the floating point unit is not enabled in the guest status register, then the coprocessor unusable exception is taken in guest mode. If it is not enabled in the guest status register and not enabled in the root status register, then a coprocessor unusable exception is taken in root mode. A coprocessor 2 follows the same rules but uses the coprocessor 2 fields in the root config 1 and status registers. If the floating point coprocessor is shared by root and guest context, so the hypervisor will need to save the floating point registers on a guest context switch. The hypervisor will need to read the floating point register mode field in the status register to decide if 32 or 64-bit floating point registers need to be saved on a guest context switch. If FR equals 0, there are 32 32-bit registers to save. If FR equals 1, there are 32 64-bit registers to save. The ability to change FR in user mode is controlled by the setting of the UFR bit in the config5 register. If this bit is set, then code operating in guest user mode can make a change to the guest status FR field, which is not visible to the hypervisor. To alert the hypervisor when a guest user might have changed FR, a GFCS exception is raised to the root on any access to the guest config5 UFR field. If this access changes UFR to a 1, then the hypervisor will need to check the guest status FR field each time before it saves the floating point registers. If the MSA mode is present, it is shared by both guest and root context. The high and low registers and the 3 additional high and low accumulator pairs need to be saved on guest context switch if the MSA module has been enabled for that guest. The hypervisor controls the access to the guest MSA module by setting the normally read-only MSA field in the guest config5 register. When an MSA instruction is issued from guest mode and the MSA module is not enabled, then an MSA module state unusable exception is triggered in the guest mode. If it is enabled in the guest config5 register and not enabled in the root status register, then the MSA module unusable exception is taken in root mode. Here is the whole picture to review. If you have shadow register sets, it's a good idea to assign at least one for guest use, so when the processor switches to root mode or when you context switch out a guest, you will not have to save its GPRs. Multiplier result registers are accessible in user and kernel modes and are not protected. These shared registers must be saved and restored if necessary. Address translation is performed first using the guest TLB and then through the root TLB. Note that the root context segmentation configurations are not used when translating a guest address. The root context TLB translates every address from the guest. Access to the FPU is first checked in the guest context and then in the root context. Exceptions detected by the guest context are handled in guest mode. Guest timekeeping and interrupts can be passed through by the root context so that the guest OS can handle them directly. Exceptions detected by the root context are handled in root mode by the hypervisor. In a multi-core system, each processor behaves just like a single processor with a root and guest context. Each processor runs a distinct hypervisor. Hypervisor instances communicate with each other to achieve shared goals as in a traditional SMP system. This can be done through shared memory segments, inter-thread communication, inter-processor interrupts, or a combination thereof. In a multi-threaded single-core system, each VPE behaves just like a single processor with a root and guest context. Each VPE runs a distinct hypervisor. The same as a multi-core system, the hypervisor instances communicate with each other to achieve shared goals as in a traditional SMP system. Note, MT module registers are never present in the guest CP0 context, so a guest cannot emulate an MT core. This concept can be further extended to a multi-threaded multi-core system. Each processor core features multiple VPEs, each of which has its own guest context. A distinct hypervisor instance is present on each VPE and in control of the root context. All hypervisors will communicate with each other over a shared channel. This last section goes into more detail about the CP0 register changes for the virtualization module. It covers the added CP0 registers and CP0 registers with new fields. The root CP0 registers are a superset of the normal processor's CP0 registers with the addition of the new registers to control guest mode and some registers which have added fields. These changes are only found in the root CP0 registers and not in the guest CP0 set. The guest CP0 registers are defaulted to the same values as the root CP0 registers on initial boot up. The guest CP0 registers are reconfigurable by the hypervisor. It can change some of the register fields in the guest CP0 registers that would normally have been hard-coded and read-only. This allows the hypervisor to give a guest OS a subset of resources available in the actual processor. Here is a table of the new registers added to the root CP0 register set. These registers are only available to the hypervisor in root kernel mode. These registers configure the amount of control the hypervisor will have over the guest OS. The guest OS will not be aware of any intervention by the hypervisor. Each will be covered in detail in the next slides. The next slides will cover fields in the CP0 guest control 0 register. The processor is in guest mode when the root exception, error, and debug bits are all clear and the GM bit is set in the guest control 0 register. The hypervisor will use this bit to transition the processor into guest mode. It is recommended the hypervisor use a return from exception instruction to enter guest mode. The hypervisor sets the GM bit, stores the starting address for the guest execution in the root EPC register, and makes sure that the guest status ERL bit is set to 0. Then it would execute the ERET instruction, which will cause the program counter to be set to the address that is in the root EPC register and the exception level bit EXL bit to be cleared in the root status register. After the ERET instruction is executed, the processor will be in guest mode fetching instructions from the PC. The RI bit gives the hypervisor control of what to do when a reserve instruction exception happens. A reserve instruction exception occurs when a reserve or undefined major opcode is executed or a value in the function field is illegal. For example, if a program were compiled to use hardware floating point and there is no hardware floating point hardware, then a reserve instruction exception would be raised if it tries to execute a floating point instruction. In this example, if the IR bit were 0, then the guest OS can directly resolve the exception and, for example, emulate the floating point instruction. If RI were set to 1, the hypervisor will receive the exception and take the appropriate action depending on the security policies it follows. The MC bit gives the hypervisor control when external hardware changes the status of the EXL field in the guest status register or the guest software changes the processor's operating mode. The hypervisor would use this exception to monitor when the guest OS is externally forced into guest kernel mode on exception or when the guest OS transitions from user mode to kernel mode, which happens with the execution of a system call instruction. The CP0 bit gives the hypervisor control of what happens when a guest privilege sensitive instruction is executed. If the CP0 bit is set to 1, guest execution of privilege sensitive instructions are permitted subject to other configuration settings. If CP0 is clear, then the use of a privilege sensitive instruction will always cause an exception. The hypervisor can choose to directly control the guest MMU. Setting AT to 1 allows root to control the guest address translation directly. AT normally defaults to 3, allowing the guest OS to control the guest TLB. However, this is implementation dependent. If the GT bit is cleared, the hypervisor will monitor all accesses to the guest count and compare registers. The cache is not protected by guest ID, so entries in the cache should be monitored by the hypervisor to be sure one guest is not corrupting or snooping another's cache or the cache entries of the hypervisor. If the CG bit is 0, a guest privilege sensitive instruction exception will result any time a guest issues a cache instruction. If CG is 1, cache instructions that use an effective address will be allowed without causing an exception. This should be secure because the effective address is translated by the MMU to a physical address, and the physical address is then used to address the cache. In this way, only addresses that were assigned by the hypervisor to the particular guest can be accessed by this type of cache instruction. Guest config 0 through 7 register writes can be monitored by the hypervisor. If cleared, writes will cause a guest privilege sensitive instruction. If set, writes by the guest OS are permitted without causing an exception. The G1 bit determines if the guest control 1 register has been implemented. This determines if you can use guest IDs. These IDs are used in identifying which guest an external interrupt is for, which guest a TLB entry is assigned to, and which guest OS is resident at the current time. These bits are implementation dependent and not defined by the architecture. The G0E bit determines if the guest control 0 EXT register has been implemented. This register gives the hypervisor more control over cache instructions, CP0 state changes, writes to additional CP0 registers. There will be more on this when I cover the guest control EXT register. The PT bit determines if the pending interrupt pass-through feature has been implemented. If this bit is set, external interrupts are passed through from the root context if enabled by the mask in the guest control 0 PIP bits. This is the way the hypervisor allows the guest to directly handle an external interrupt without hypervisor intervention. If the processor includes the MCU ASE, which expands the number of interrupts from 6 to 8, then these bits will be used as part of the pending interrupt pass-through mask. This is the mask of interrupts that will be passed through to the guest OS without hypervisor intervention if the processor is in non-EIC mode. If a bit is set, the external interrupt will be directly handled by the resident guest OS. This mask is enabled or disabled by the PT field in this same register. The root ASID field de-aliasing mode can be used if there is only one guest possible. Then the hypervisor could use the ACID in the root TLB to distinguish entries belonging to the guest OS or the hypervisor. This is not recommended if there is more than one guest possible, because the root TLB would need to be cleared when the hypervisor switches between guest contexts. In the case where the RAD field is set and the global bit is also set for the TLB entry, then that entry will be valid for both the root and guest contexts. You could also think of this as determining if the TLB is shared. If it is set to 1, the TLB is not shareable between different guest OSs. Note, if this bit is 0, then the hypervisor must use guest IDs in the TLB entries, so the G1 bit in this register must be set, indicating an existence of the guest control 1 register, which contains support for guest IDs. Conversely, if this bit is 1, then the G1 bit will be cleared and the guest ID cannot be used. When the processor uses guest IDs in the TLB entries, and it is in the root mode but not in error, exception, or debug mode, setting the DRG bit will cause loads and stores to use TLB entries associated with the root control guest ID that is set in the guest control 1 RID field. In other words, this switches the hypervisor from using root TLB entries to using guest TLB entries when executing in normal mode. The G2 bit indicates the presence of a CP0 root guest control 2 register. This will always be set if the processor uses an external interrupt controller and may be set if it does not. If the processor is not in EIC mode, then the hypervisor will use the root guest control 2 register to assert and deassert virtual interrupts to the resident guest OS. If the processor is in EIC mode, then the root guest control 2 register will facilitate the hypervisor with interrupts that should be routed to the guest OS that is not currently resident. When the root cause GE bit is set, a hypervisor intervention exception has occurred. The GE code field further qualifies this exception. 0 is a guest privilege sensitive instruction. This happens when the execution of a guest privilege sensitive instruction was attempted from guest kernel mode, but the instruction was not enabled for the guest kernel mode. 1 indicates a guest software field change event has happened. 2 indicates a hypercall instruction was executed by the guest. 3 indicates that a guest is getting a reserve instruction exception and the guest control RI bit is set, causing the exception to be redirected to the root context. GVA indicates that a guest mode access resulted in a root TLB access and the guest physical address is not available. Root bad vAddr is set to the guest virtual address. This is allowed for a non-TLB refill exception. For example, if a store was done to a clean page, the dirty bit is not set, so the translation in the TLB is correct, and the exception is just telling the OS that the page is being written to for the first time. In this case, an implementation is allowed to set the root bad vAddr to the guest virtual address. The root TLB exception handler should check this bit and see if it is set. If it is set, it must probe the guest TLB entries using the TLBGP instruction to find the index into the guest TLB that contains the guest virtual address. Then the handler would use the TLBGR instruction to read that index entry in the guest TLB to determine the guest physical address. The handler would then use the guest physical address as the virtual address in finding the entry in the root TLB. For this example, it can then set the entry's dirty bit. Note, MIPS core implementations use this method because it preserves the micro TLB entry and avoids a load miss for future loads. 9 indicates the guest hardware field change event happened, and 10 indicates that the guest mode accessed resulted in a root TLB access and the guest physical address is available. The root bad vAddr will be set to the guest physical address. This will always be the case for a guest TLB refill exception, which will always set the GPA in the guest control 0 GEX code. If the GPA is set, the root TLB exception handler can use the root bad vAddr for the virtual address it needs to find for the translation.